Welcome to the cosmos of curiosity. Today, we're embarking on a stellar journey through the eyes of the James Webb Telescope. Our topic? HEWASRIGHT, James Webb Telescope just spotted 5 galaxies that might be older than the universe. Get ready to dive into the depths of space and unravel a cosmic mystery that's shaking the foundations of astronomy. In the vast expanse of space, the James Webb Space Telescope has dramatically altered our understanding of the cosmos. This pioneering telescope continually reveals astonishing visuals, ranging from the remote corners of the universe to the planets within our solar system. A year ago, we were introduced to its capabilities, and the results were stunning. Among the highlights were the mesmerizing images of the Carina Nebula, Stephan's Quintet, and the Deep Field, which displayed thousands of galaxies extending into the distant universe. However, the most extraordinary discovery by the James Webb Telescope is the existence of enormous mature galaxies far back in time. Galaxies so ancient they seem to predate the universe itself, earning them the moniker universe breakers. These enigmatic galaxies were unexpected and defy current scientific understanding of their formation. This raises a crucial question. Are the Big Bang Theory and modern cosmology facing a crisis? Join us in exploring how the groundbreaking findings of the James Webb Telescope might radically alter our fundamental theories about the universe's inception. The concept of the Big Bang originated from a simple theory, evolving from 3 key observations underpinned by Einstein's general theory of relativity. Firstly, any universe with a uniform spread of matter and energy cannot maintain a static state. It must either shrink or grow. Secondly, through observation, we see galaxies like spirals and ellipticals beyond the Milky Way, whose distances we can measure. Thirdly, the light from these distant galaxies shows a redshift, more pronounced the further away they are, suggesting an expanding universe. These 3 insights lead us to believe that if the universe is currently expanding and becoming less dense, it must have been smaller, denser, and more uniform in the past. This idea of an initially dense, compact universe was first synthesized by George Lemaitre in 1927, and later independently by Howard Robertson in 1928, Edwin Hubble in 1929, and Arthur Walker shortly afterwards. ACV developed. We understood that the early universe was not just denser, but hotter. As it expanded, it cooled, leading to predictions of a pervasive low-energy radiation with a black body spectrum everywhere, a remnant from when the universe cooled enough to form neutral atoms. This hot, dense state would have initiated nuclear fusion before the formation of stars, resulting in a primordial mix of elements beyond hydrogen. The formation of neutral atoms marked a shift, enabling the universe to start clustering into the structures we see today. The universe is a grand tapestry, composed of stars, star clusters, gas clouds, galaxies, galaxy clusters, and the vast cosmic web with its filaments and voids. These elements, integral to the Big Bang Theory, have been repeatedly confirmed, invalidating many alternative theories that fail to account for these phenomena. Recent advancements have introduced 3 additional components essential to our understanding of the universe: dark matter, dark energy, and cosmic inflation. Dark matter, unlike normal matter, gravitates and clumps together, but does not interact with normal matter or light. Dark energy, on the other hand, is a mysterious force inherent to space itself. Cosmic inflation is a critical concept that defines the limits of our ability to trace back the universe's history before matter and radiation ceased to be the dominant forces. This comprehensive understanding allows us to do something extraordinary. Inflation theory helps us outline the initial conditions of the universe at the onset of the hot Big Bang, its initial temperature and density, the spectrum of initial density imperfections, which were adiabatic Gaussian random fluctuations, and the scale of these fluctuations across the cosmos. By integrating the standard model of physics with the concepts of dark matter and dark energy, we can define the various types of energies and their abundances throughout the cosmic timeline, from the very beginning. The capability to trace the development of the universe from its earliest conditions following the hot Big Bang to the present day is a cornerstone of modern astrophysics. Through both theoretical predictions and numerical simulations, we explore the evolution of an expanding universe that originated from a hot Big Bang, equipped with the characteristics we've deduced it should possess. Despite the wealth of observational evidence supporting this model, its completeness is continually tested. The recent introduction of the James Webb Space Telescope has significantly expanded the toolkit available to astronomers. This cutting-edge instrument has raised questions about the Big Bang theory as it observes early universe phenomena that current cosmological models struggle to explain. The James Webb Space Telescope represents a leap forward, providing humanity with its first high-definition view of the infrared universe. Its advanced capabilities are revealing galaxies from the earliest stages of cosmic history. Before the James Webb Space Telescope, our knowledge of early galaxies was limited. We had one confirmed galaxy, Gien's 11, dating about 400 million years post-Big Bang, and only one other potential galaxy from around 330 million years after the Big Bang. With the advent of the James Webb Space Telescope, the depth of our cosmic understanding is set to expand significantly, offering new perspectives on our universe's ancient past. Observations of galactic signals from such early periods in the universe were once considered unattainable. However, since the James Webb Space Telescope commenced its scientific operations over a year ago, the narrative has shifted dramatically. We now have over 100 galaxy candidates from James Webb that date back to the universe's first 400 million years, and several have been confirmed as incredibly distant and ancient. Gien's 11, once the most distant known galaxy, now ranks 5th. The current record holder for the most distant galaxy, JZG's 13Z, dating from just 320 million years after the Big Bang, is expected to be surpassed soon. We anticipate the discovery and confirmation of dozens of new ultra-distant galaxies in the coming months. These early galaxies uncovered by James Webb display unusual and perplexing characteristics that seem challenging to align with our theoretical understanding of the universe. They are notably massive, luminous, rich in heavy elements, actively forming new stars, and abundant in gas. The prevalence of such galaxies in the early universe is a conundrum. Our current models of how gas accretes onto these primordial galaxies and how star formation impacts future gas accretion suggest a limit to the rate at which material can gather around these celestial bodies. While certain conditions might allow a galaxy to temporarily exceed this accretion limit, sustaining such growth over extended periods challenges our existing knowledge. Therefore, as we continue to observe and analyze these early galaxies, we confront the possibility of revising our theories to accommodate these new findings. As we delve into the study of these extremely early galaxies, observed by the James Webb Space Telescope, we encounter findings that seem incongruent with existing cosmological theories. The sheer mass of these galaxies, as captured by James Webb, suggests they should not exist according to current cosmological models, leaving astronomers who subscribe to the Big Bang theory both stunned and perplexed. The Big Bang theory posits that the universe's galaxies originated from primordial dust following a massive explosion. However, the revelations from the James Webb Telescope are now challenging this widely accepted theory, sparking debate and reconsideration among the scientific community, particularly those who support the Big Bang as the origin of the universe. The traditional view of Big Bang scientists is that the expansion of the universe originated from a singularity that exploded billions of years ago. While some galaxies are observed to be moving away from us, a phenomenon known as redshift, this does not necessarily apply universally. In fact, not all scientists, including those studying evolutionary aspects of the universe, interpret redshift as definitive evidence of a universal expansion or a primordial Big Bang. There is a discourse in the scientific community, with some suggesting that mainstream science journals tend to favor research supporting the Big Bang theory. Canadian physicist David Rowland, for example, in his online article, argues against the Big Bang, citing several scientific inconsistencies that he believes are often overlooked or ignored to maintain the popular narrative of the Big Bang. The majority of scientists currently endorse the Big Bang theory, but there is a subset of the scientific community presenting alternative viewpoints. These scientists, facing challenges in publishing their theories through traditional scientific journals, have turned to the internet to share their arguments against the Big Bang theory. Among them is David Rowland, who offers a different interpretation of the red shift observed in galaxies. Contrary to the common belief that red shift indicates the velocity at which galaxies are expanding and moving away, Rowland suggests it merely reflects temperature and distance. Rowland argues that early scientists mistakenly equated the red shift from galaxies with the Doppler effect, leading them to conclude that the universe is expanding. He posits that the light from galaxies naturally weakens over long distances, a phenomenon early astronomers misinterpreted as evidence of an expanding universe. This early misinterpretation, according to Rowland, has persisted and is still widely accepted and taught. Even Edwin Hubble, the renowned astronomer after whom NASA named its famous telescope and who first observed the redshift, had reservations about interpreting this as conclusive evidence of expanding galaxies. Hubble considered alternative explanations for the redshift and was cautious about linking it directly to the expansion of galaxies. He suggested that the redshift might not necessarily imply ongoing expansion, as telescopes only allow us to see the past, not the present state of galaxies. Interestingly, the Bible also touches on the concept of an expanding universe. Various passages speak of God stretching out the heavens, which some interpret as aligning with the idea of cosmic expansion. However, Rowland points out that if the Big Bang had indeed occurred, it would have resulted in a uniform distribution of gases throughout space, a condition that seems to be at odds with current observations. The assumption that gases in the early universe lacked sufficient gravitational attraction to coalesce into planets and stars has led Big Bang theorists to posit the existence of dark matter. This hypothetical substance is believed to provide the necessary gravitational force for the formation of stars and galaxies. However, the existence of dark matter remains unproven scientifically, and its hypothesis has faced increasing skepticism in the scientific community. Big Bang proponents argue that dark matter is the only viable explanation for the gravitational behaviors observed in galaxies. Nonetheless, alternative theories have been proposed. One such theory is modified Newtonian dynamics, MOND, which offers a different explanation for these galactic phenomena without relying on the existence of dark matter. This theory challenges the notion that 80% of the universe must be composed of dark matter to account for the observed movements and behaviors of galaxies. Dr. Duane T. Gish, a creationist scientist, has expressed doubts about the capability of even hypothetical cold dark matter to explain the formation of the massive galactic structures discovered in recent years. He also pointed out that an explosive event like the Big Bang cannot adequately account for the precise and orderly orbits observed in the countless stars and galaxies. While gravity might explain how this order is maintained, Gish argued that it does not sufficiently explain the origin of such a complex and organized cosmic system. The complexity and order seen in the universe present a stark contrast to the disorder that might be expected from chance and random processes. Some argue that this order can only be rationally explained by the presence of an intelligent power. In the field of evolutionary astronomy, there are theories suggesting that trillions of stars have collided, leaving the survivors to establish precise, orderly orbits. However, this notion raises questions about its rationality. If such a massive collision of stars had occurred, it would likely result in a significant residue of gas clouds in space. The current observed levels of gas and dust do not support the scale of stellar deaths required by this hypothesis. It seems more plausible that stars decay into gas clouds and dust, rather than the reverse, as traditionally taught by evolutionary astronomers. Evolutionary astronomers often posit that structures like the so-called pillars of creation are stellar nurseries. However, this remains an assumption often presented as fact in textbooks and media. In an effort to reconcile observations from the Webb telescope, scientists have proposed a hybrid model. This model merges elements of the tired light model with a cosmological model based on evolving coupling constants, suggesting a more extended timeline for galaxy formation. This would allow for the existence of well-developed early galaxies, but further research is needed to validate this theory. The scientific community has a history of adapting and evolving theories in light of new observations. Albert Einstein's explanation of light's particle-like and wave-like nature is a classic example, and the estimation of the universe's age based on the age of stars in globular clusters is another approach. In summary, the discrepancies between current observations and the standard model of cosmology have led to the proposal of a new model that implies a longer age for the universe. While this new model is promising, it requires further exploration and validation to ascertain its efficacy in explaining cosmological observations. The ongoing quest to validate a new cosmological model that can comprehensively explain all observations continues, and in this endeavor, the James Webb Space Telescope plays a crucial role. Recently, it made a significant discovery, identifying two of the most distant galaxies ever observed. These findings bolster the foundational concepts of galaxy formation as outlined by the Big Bang theory. This remarkable discovery was facilitated by a cosmic phenomenon known as gravitational lensing. A massive galaxy cluster, Abell 2744, also known as Pandora's cluster and situated about 3.5 billion light-years away, acted as a gravitational lens. The cluster's immense gravity warps spacetime, amplifying the light from more distant galaxies. Benji Wang, a member of the James Webb Space Telescope team from Penn State Eberly College of Science, utilized the telescope's advanced near-infrared spectrometer and camera to search for early galaxies magnified by this cosmic lens. During their observations, Wang and her team discovered two galaxies with exceptionally high redshifts. The concept of cosmological redshift involves the stretching of light wavelengths due to the ongoing expansion of the universe. The farther away a galaxy is, the more its light has been stretched while traveling across space, shifting from shorter, bluer wavelengths to longer, redder ones, eventually moving into the invisible infrared spectrum. Galaxies that formed between 300 and 400 million years after the Big Bang have had their light stretched into these infrared wavelengths. Using the James Webb Space Telescope's advanced instruments, the team identified the lensed images of two high redshift galaxies. One, designated UNCOV-ERZ13Z, with Z's indicating redshift, has a redshift of 13.79, making it the second most distant galaxy known to date. The most distant confirmed galaxy, as of now, remains J-ADES-Gs. In 2022, the James Webb Space Telescope made a groundbreaking discovery with the identification of the galaxy J-ADES-G zone 130, which has a redshift of 13.2, making it one of the most distant galaxies ever observed. Alongside this, the telescope also discovered UNCOV-ERZ13, which is seen as it was just 330 million years after the Big Bang, and UNCOV-ERZ12 with a redshift of 12.393, placing it fourth in the list of most distant galaxies, seen as it was about 350 million years post-Big Bang. What sets the two UNCOV-ER galaxies apart is their distinct appearances, unlike other galaxies observed at similar redshifts, which tend to be point-like and very small. The UNCOV-ER galaxies, however, display notable structure. Benji Wang, a member of the James Webb Space Telescope team, noted that while previously discovered galaxies at these distances appear as dots, one of the UNCOV-ER galaxies resembles an elongated shape, almost peanut-like, and the other appears fluffy and spherical. Additionally, UNCOV-ERZ12, exhibits a sizable edge-on disk, spanning about 2,000 light-years, which is significantly larger than other galaxies observed from this era. The variation in size among these early galaxies raises questions about their star formation and subsequent development. Wang finds the diversity in galaxy properties at this early stage intriguing, as these galaxies are believed to have formed from similar materials but are already showing markedly different characteristics. Despite the differences, both of these newly discovered realms align with the general principles of the Big Bang model. This model explains how galaxies began forming in the aftermath of the universe's creation, offering a framework for understanding the early stages of cosmic evolution. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions, updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment